So, hi everyone. First of all, I would love to thank you all for being here today. My name is Naouel Haggui, and today I'm going to present my paper entitled OpenVVC decoder Parameterized and Interfaces Synchronous Dataflow Model Tile-Based Parallelism. Through this presentation, we are going to start with an introduction in which we are going to have a small talk about both field, video coding, and data flow modeling. Then we have to focus on VVC decoder structure and its parallelism strategy. Followed by that, we will talk about the proposed data flow model and its experimental result and interpretation. And finally, some conclusion and perspective. Video are taken all over the world. It's projected to account 82% of global internet traffic by 2023. Actually, we can all note the huge use of video streaming websites such as Netflix, YouTube, the huge use of gaming platform, and the most important, the huge use of video conferencing nowadays, especially since the appearance of COVID-19, which forced us to stay at home and remote working, unfortunately. And through years, multiple video new format has appeared. Thus, also there is new video standards, such as AVC that target HD resolution, also EVC that target 4K and Ultra HD resolution, and finally, versatile video coding VVC that could target 8K resolution. This codec has been released in July 2020. Compared to the previous one, EVC, it enabled 14 to 15% of coding gain for the same visual quality. And this is the standard that we are going to work with. It is true that VVC has enabled a lot of adventures, such as support for new video formats. It is easily reconfigurable for various application performance. However, it has some drawbacks. The computational complexity in both sides, encoder and decoder, has increased. So we need optimization to cope with real-time applications. So a lot of research has been conducted in order to reduce that. Some of them by using machine learning, especially in the encoder side, the partitioning part, the prediction part, and other by exploring parallelism between tasks, which is the focus of this paper. Actually, since the appearance of Moore's law, the industry have moving toward the creation of multi-core algorithm, as the modern application exceeds the capability of single-core architecture. So we need to create multi-core algorithm. However, the creation of multi-core algorithm is not that easy. So we need a design methodology that facilitates this task. One such methodology is data flow modeling. What is it? Well, data flow is a network of computing unit called actor exchanging token through unidirectional buffered links, FIFOs. Why we choose data flow? Why? Well, because it is a methodology that's proven to be useful for capturing important data dependency, exploring parallelism between system core, and the most important thing, that with the same data flow model, we could target different architecture, like such as x86, Array, FPGA, etc. So the purpose of this work is to create a data flow model for the VVC decoder. In order to create the model, there are some things to know first. One of these things is the structure of the decoder. And the most important thing is to know how to, what are the parts that could explore in order to pop up parallelism. So to answer the first point, which is the structure of a decoder, may you please have a look at this picture. You could notice that there are three main parts of a decoder that are entropy decoding, block reconstruction, and finally in-loop filters. The entropy decoding is based on the use of CABAC that transform binary syntax into non-binary syntax and feed all other parts of the decoder. Then the block reconstruction will be responsible in reconstructing the different part of a frame. Finally, the in-loop filter that are DBAF, SAO, ALF will be responsible for removing those the artifacts. Now, with the most important question, How to pop up parallelism? Well, VVC enables 3 levels of parallelism that are data level parallelism, frame level parallelism, and high level parallelism. For data level parallelism, it is based on SMD instruction, which enable the use of the same operation on multiple data points, which mean application that uses vectors and matrix. For example, the transform unit over there could be really a good target to optimize with this instruction. The second level is frame level parallelism, which obviously going to use the independency between frame and decode them in parallel. And the final level, which is tile level parallelism, and which is interested for which is the focus of our work, it is based on the independency between tiles. Actually, tiles are rectangular region of a frame, as VVC enable the partitioning of a frame into different parts. Could these parts be decoded and processed independently? The answer is yes. How so? Well, because the prediction dependency across tile boundary are broken and the entropy encoding is essentialized for each tiles. So which means it is perfectly possible. A small other investigation to do before creating our model is to know the different decoder that are used in the VVC, compliant with the VVC standard. Our small research, we found out that there are mainly 3: VTM decoder, VDEC decoder, and OpenVVC decoder. In this work, we decided to go with OpenVVC decoder, as it is the decoder that take benefit of the 3 parallelism level that I mentioned. And also, compared to the other one, it has better performance. What is OpenVVC? Well, it is a software decoder complete with the VVC standard. It is based on C programming language and integrated as a dynamic library with FFmpeg player. I put a link over there. If you'd like to know more about it, go for it. And after that investigation, we implement the OpenVVC project as an external library in Prism project. Prism is the tool that we are going to use in order to create our data flow model. Then we disabled the use of all functions developed using pthread in the OpenVVC project, and we were able to create this model. As you can see here, there are different and several actors. For example, the one on the left is attached file stream, attached stream actor, which will be responsible on attaching the bit stream to be decoded to the decoder, initialize the demixer and the decoder, and send those information to the other actor via OVVC HDL variable. Then the frame information extraction actor will be responsible on extracting the different information of a frame, especially the null units, and will be sent via a variable PU, which is a vector of null unit, to the frame decoding actor, which will decode the frames, obviously. And the process continue until we reach the detached stream actor, which will close the file, which is the bit stream, and reinitialize the demixer to 0. As I mentioned before, we are here interested on tile level parallelism, and tile are part of frames. So the frame decoding actor is an hierarchical one, which means that the inside there are many other actors. Sorry. The most important one over here is tile decoding actor. In order to ensure the parallelism, we use tile number parameter. It's the blue one over there. If n tile number parameter is equal to n, the tile decoding actor will be duplicated n times, and those n times tasks will be executed in parallel, and thus the tile level parallelism is there. It is important now to testify our model. It is working or not working. So and to do so, we need bitstream that contains tiles. So we used VTM 12.0 encoder in order to create those byte stream. So we used the Ultra HD and Full HD sequences. Those are the sequences that have the highest resolution. And with the growing complexity of VVC standard, there is a critical issue, especially for high resolution sequences. And also with high resolution comes high granularity of actor, which is important in order to have a good result while using with x86 architecture, which is the case in our work. So we were able to create different bit stream with the three tile configuration that are 4x3 splits, 4 horizontal by 3 vertical splits, 6x2 and 6x4. So we use the same encoder configuration without tile in order to calculate the BD rate objective measurement. As you can see here, as the number of tile increases, there is an increase in the BD rate also, which means a bit rate overhead for the same quality. Also, previous study shows that with the increase of number of tiles, there is a decrease in equality, which means actually, and this is due to the fact that the prediction dependency across tile boundary are broken and the entropy encoding is initialized for each tile. So there is a loss of information, so a loss of quality. So we were able, now the bitstream are ready, the decoder are ready, so we start to have some results. And to compare with the OpenVVC, we disabled the use of frame level parallelism in order to keep it fair to compare with our model. So the comparison here is made only on tile level parallelism. As you can see here in both figure for Full HD and Ultra HD, the OpenVVC performance and our model were assessed on various bitrate values for KP equal to 22, 27, 32, and 37. For both results, we achieved a result that is slightly above that of OpenVVC. We achieved, for example, speed up equal to 7 while using 12 tiles on 12-core x86 architecture for full HD sequences. Same over here, where using 24 cores and for full HD sequences, for example, with 24 tiles, we achieved a speed up equal to 11 while using 24 core. You may think that having a speed up equal to 11 on a 24 core, it's not that good. Maybe we have to obtain 24. But this is not true. How so? Because the decoding process is not 100% parallelizable. Actually, it's mainly sequential. That's another factor that explains the discrepancy between the theoretical case and our obtained result is the fact that tile doesn't have the same sizes. As you can see here, for example, in the figure on the left, you can notice that for the tile number 1, for example, the CTU number are bigger than those of the final tiles. Another fact that we know that for each frame, the details differs from one pixel to another. Consequently, it differs from one CTU to another, thereby from one tile to another, which means that the decoding time for each tile will differ also. And that's shown by the figure on the right, which shows the per tile decoding time in percentage for a frame of Picket to rest sequences. As you can see here, for example, tile number 24 show a decoding time higher than this of tile number 2. However, it is true that our model is slightly above that of OpenVVC, but doesn't really outperform it. However, this is not the real important of using data flow modeling. Let me explain. Imagine that you are using pthread or OpenMP or OpenCL to create a multi-core algorithm for an X architecture. You will need months and months of development. And this is for a target architecture. So if you need to use the same multi-core algorithm on another architecture, you need to create a new one. So months and months of development, and the circle goes round and round. However, with the use of data flow model, you have one model that could target all architecture, and this is the power of data flow modeling. Another result up for debate is the time spent by our data flow decoder on a single core architecture. Actually, several data flow models for other decoder has shown promising result while using multi-core. However, it wasn't the case on a single core. It shows decrease while on a single core compared to the reference decoder. As for example, RVCal model for HEVC standard that shows 15% less efficient than HM 9.0 and 5 times less efficient than Open HEVC. Same for another data flow model, a data flow model for a full decoder that explores parallelism between the Greg UV component, has shown lower FPS compared to the reference decoder, and OpenHEVC has outperformed both. In our case, our data flow model has shown a competitive result on a single core to OpenVVC, and both of them, that our data flow model and OpenVVC, show a result better than the reference software, which is VTM 12.0, which means that our models still perform also well on a single core architecture. So to conclude, this work has revealed the importance of data flow modeling. Data flow modeling, actually the creating of a multi-core algorithm using data flow modeling requires a shorter development time compared to the state-of-the-art approach such as OpenMP and OpenCL. And data flow modeling is an effective framework that facilitates the transition from software to hardware. And as a perspective, we aim to improve our model in order to support frame-level parallelism also. And we aim to adopt task-based code generation in execution method to automatically balance the difference of tile decoding time, as I already presented before. And we aim to perform a memory user study for both OpenVVC decoder and our data flow model. So this was my presentation. Thank you for your listening.
Do we have any questions?
Thanks for the presentation. I was wondering, the experiment that you presented, the number of tiles was equal to the number of cores. Did you consider having small size tiles to already perform the load balancing and also maybe matching the memory hierarchies that you have on your system?
So actually, if you use a small number of tiles, you're not going to have a good result because we are working on an x86 architecture. So we need to have a coarse grain granularity. So while increasing the number of tiles, we decrease the granularity of our actors. So we wasn't able to obtain good results. However, with increasing of the number of tiles, we obtained better results. And also, as we are interested in tile level parallelism, we were interested on using multiple number of tiles. And the choice of a tile number equal to the number of cores was to show the difference between theoretical case and our results. So for a 1% parallelizable application, if we used 12 tile, we aim to use 12 speed up equal to 12. So that's why we choose the same number.
Okay, thanks.
So thanks for the nice presentation. I have a question on the model itself. So do you have some things that you feel are missing from the model, and what has been the most difficult to describe with the model when you've been so you've started from C++ code and you have needed to merge your application into this model? Do you have some features that you would need to do it more efficiently?
Actually, at the beginning, the most difficult part was to implement the OpenVVC library as an external one in our project of Prism. That was a point. And the other point that was caused a little bit a problem was adding the delays to our actor. So we have to try many things in order to decrease those delay and don't have a problem in our model. So.
Okay, thanks.